से करनी है माइक आपका पॉइंटर दे दो ये सारे लोग ये रहा नहीं इनको भी वही लगा रहा होगा सामने नहीं कर रहा हूँ इन लोगों को आए नहीं लोग कुछ नहीं रोड में वैसे ही कह रहा हूँ मुमताज पॉइंटर ये रहा ठीक है Auzubillahi minash shaitanir rajim bismillahir rahmanir rahim. So today we are going to have a lecture of Professor Zahid Qamar from Sultanate of Oman, Sultan Qaboos University. The topic for today's lecture is challenges, opportunities, and future trends in engineering education. So I'll briefly introduce Professor Sayyid Zahid Qamar. He is a professor of mechanical engineering department at Sultan Qaboos University, Oman. He has over 30 years of academic and research experience in different international universities. He has also worked as a professional mechanical engineer for over 6 years in heavy engineering and fabrication industry. And he has a lot of his research areas are applied materials and manufacturing, applied mechanics and design, reliability engineering, and engineering education. As part of the applied mechanics and advanced material research group at Sultan Qaboos University, he has been involved in different applied research funded projects in excess of $4 million. He has over 255 research technical publications to his credit. He has also edited few books, volumes, chapters, publication in refereed international journals and conferences. He has served as associate editor, guest editor, and member editorial board of different research journals, including materials and manufacturing processes, Journal of Elastomers and Plastics, and the Journal of Engineering Research. So I would request Professor Sayyid Zahid Qamar for his lecture today at Comstech. Welcome to Comstech, sir, and we'll move on to your lecture today.
Thank you, Dr. Harris, for a detailed introduction, and lots of thanks to Comstech in general and to Professor Iqbal, who personally invited me to be here. It's a real pleasure to be with you. My name is Sayyid Zahid Qamar. Today's topic is challenges, opportunities, and future trends in engineering education. As Dr. Harris just told you, I work at Sultan Qaboos University in Muscat, Oman. My department is mechanical and industrial engineering, but inside the department, there is a research group, applied mechanics and advanced materials, which we call AMS squared. We are part of that. Before we go into the topic, I would just want you to have a quick look of Oman. It is next to Saudi Arabia, Yemen, and United Arab Emirates on one side. I went there thinking that I'd stay for a couple of years, but I've been there for 18 years plus. And this geography that you are seeing, I thought it would be a desert, but there are beautiful places inside. You can see some of these views. I got enchanted. I stayed there, and I would want you to keep on the lookout for any conferences being announced in Muscat region. And if you come, we could be your hosts, and you would really enjoy it. It's a very, very beautiful place. This is the Muscat Corniche. This is my university, Sultan Qaboos University. It's the largest in the country. Some of the views of the university, and so on. So with that, we jump into today's topic. We are talking about engineering education. Long time ago, people who sacrificed their sleep, family, food, laughter, and other joys of life were called saints. Now they are called engineers. So hopefully I'm addressing all these very dedicated engineers around the world, whether they are in the field or related to academics in engineering. But because it is engineering education, so I would like to share with you a quotation from Chesterton. Education is the period during which you are being instructed by somebody you do not know about something you do not want to know. Right? Hopefully that is not always true, but that's the tough task that instructors have to face, right? That they have to make whatever technical knowledge they are presenting very palatable and interesting to the students. As an introduction, engineering contributes significantly to the economic well-being, social stability, and cultural development of society. We definitely know that. engineering also plays an important role in global human development, sustainability, and preservation of the environment. Local level, national level, global level. Therefore, there is a huge importance of high quality engineering education. Now, gleaning from my personal experience as a professional field engineer and a university educator, both, this paper or presentation highlights the recent challenges, opportunities, and future trends in engineering education. As the topic would suggest, it's a very broad topic, so we would touch only on a few of the things. We can continue talking about it in much more detail some other time. What is good engineering education? The target of good engineering education is to produce engineers who can make a meaningful contribution in the face of evolving technology and society. That's very important, right? I mean, education should not be that now this is where you are, and if things change, you cannot adapt, right? Evolving technology, evolving society, and engineers should adjust themselves to it. The National Academy of Engineering in the US, its president, Dr. Mote, there was a review of history of engineering at a workshop on pathways for engineering talent that he did for NAE in 2014. And he said, every engineering field was essentially formed to get the knowledge and know-how to execute tasks that were necessary for the community to make progress, right? So this is a very general definition of engineer. Not that you can run the machines that are there now, but can you contribute to future development and progress? Then you are really and truly a good engineer. Today, the world is witnessing huge and rapid technological change, we know that. And there are major shifts in global engineering trends. The fundamental question is, are engineering programs and curricula in the universities adapting well to these changes, to the requirements of occupational flexibility of engineering graduates? And are they adapting well to meet the current and future demands for engineering skills and knowledge? So today's engineers must have a strong mix of technical, professional, and soft skills. That is the core that all engineering institutions must address to, that it is not technical knowledge that they are providing. They must make very good professionals and all the required soft skills together with it. We will talk about a few of them shortly. In addition to traditional basic courses in mathematics, physics, and chemistry, many engineering programs are therefore now including information and computer technology, biological, social, and behavioral sciences, and humanities into their core curriculum, right? Non-technical courses, but required. ABET, if you know, I mean, some universities in the world are accredited by ABET. It was originally Accreditation Board for Engineering and Technology. Now they have dropped the long name. They are just known as ABET. In their 2017 report, they said that the number of accredited bachelor's programs in bioengineering and biomedical engineering in the US witnessed a 400% increase in the last 15 years. So this is just one example that traditional engineering is on one side, but if the world knows that we are going towards biomaterials and biomedical engineering, then in advanced countries, there is a 400% increase in the universities. Do universities in our countries similarly make plans for the future? So now we will talk, as I just said, the professional skills and the soft skills on the other side. In early 1900s, I'm talking about more than 100 years ago, high-tech industries of that time stressed the need for a well-rounded, or what they call a T-shaped worker, not a serial worker, a worker who would go in one direction and then at 90 degrees to it. So they wanted to combine in-depth knowledge and skills in the area of expertise with broad interdisciplinary and team-based talents. And this was a requirement more than 100 years ago. It stands true today also. In today's world, in an interview to New York Times, Laszlo Bock, Google's senior vice president of people operations at that time, he said, that the essential skills to look for in future candidates is leadership, humility, collaboration, adaptability, and love for learning and relearning, right? So just in this one sentence, he is not talking of the technical capabilities. They are definitely already there. But just imagine, right? Not just leadership, humility, right? Being down to earth and so on. So these are the qualities that they want in the future leadership of engineering. In the 1990s, increasing employer discontent with professional preparedness of engineering graduates was very much highlighted. ABET Engineering Criteria EC 2000 highlighted the key importance of professional and soft skills on top of traditional technical skills. They have a famous A to K student outcomes or abilities set. We will just show you in the table. My university, many other universities around the world, when they go for accreditation, then they go for ABET, but other places go for, say, the Washington Accord and other criteria. But this A to K, that once you graduate as an engineer, what should be the abilities that you must have to face the world? Now, recently, 2 or 3 years ago, ABET has revised and changed the 11 A to K to a set of 1 to 7 format. We are not discussing this recent change here. I will stick to the A to K format. And these are the ones. A, an ability to apply knowledge of mathematics, science, and engineering. B, an ability to design and conduct experiments, as well as to analyze and interpret data. C, an ability to design a system component or process. D, an ability to function on multidisciplinary teams. E, an ability to identify, formulate, and solve engineering problems. F, an understanding of professional and ethical responsibility. G, an ability to communicate effectively, and so on. So as we will see later on, only the first 3 are technical skills. Only the first 3, A, B, and C. All of the other 8 are soft skills or professional skills. So this is what the engineers today need to be, right? That you are very good in your technical problems and so on. Then I have just listed here the new ABET outcomes, student outcome 1, 2, 3, 4, 5, 6, and 7. For example, number 1, an ability to identify, formulate, and solve complex engineering problems by applying principles of engineering, science, and mathematics. Why has ABET gone from 11 targets to 7 when they were implementing these, just like ISO, if it qualifies an industry, then every 4 to 5 years, they come back and revisit. So ABET also every 6 years comes back and revisits and takes a look at everything that we are doing. So trying to prove that we are meeting all the 11 targets is sometimes tough. So they have reduced it to 7, but it is still a mix of the same targets. As I said, in the A to K scheme, only the first 4 skills, A to C and E, are attributes in the traditional scientific, technical, and engineering areas. The other 7 outcomes, I will definitely go through them just now, just to highlight it, are professional skills and soft skills. They are generally more intangible than purely technical. For example, teamwork, especially in a multidisciplinary context. You are a mechanical engineer, can you work with robotics? You are a mechanical engineer, can you work with systems engineering also? Effective communication, lifelong learning. Have you the ability to learn new things during your profession? Cognizance of contemporary issues. The world is changing, politics is changing, environmental issues are changing, new materials are coming in. Are you abreast of these or not? Professional and ethical responsibility. Professional responsibility as an engineer, ethical responsibilities, and so on. And impact of engineering solutions in a global, economic, environmental, and societal context. It is not enough that your solution is very viable and very good in the technical sense, but economically and nationally and globally, is it still attractive? The NAE report of 2004 says, they termed it the engineer of 2020, right? Vision of engineering in the new century. They listed 9 required attributes of future engineers. And then once they did that, because this is the National Academy of Engineers, so then people tried to do a comparison between the ABET requirements and the NAE requirements, that are they targeting the same type of skills. Then they also included the other engineering institutions like American Society of Mechanical Engineers, the American Society of Civil Engineers, the National Society of Professional Engineers, and so on, so that all the people who are making rules and regulations and policies of engineering education should be on one page. And there was a common theme that there must be a mix of technical, professional, and softer skills with emphasis on creativity and innovation and business insight. So here I have a table. If a PDF of this is available to you later on, then you can see it, that these are the NAE attributes: strong analytical skills, practical ingenuity, creativity, and innovation, good communication skills, and so on, right? And on the right, we have listed, and a very big team of professionals around the world have agreed to this, that strong analytical skills relates to ABET requirements A, B, and K, and so on. So whether you are going for the NAE list or you're going for the ABET list, you will still have commonalities between the two. So now, one or two of these we will talk about in a little more detail. I am talking of engineers, right? So they could be mechanical engineers, civil engineers, petroleum engineers. We are not talking only of electrical and computer engineers. The increasing use of computer programming and software tools in engineering has made it that there are necessary tools in design, simulation, testing, and manufacturing, right? You may be a manufacturing engineer, but if your computing skills are weak, then you can't be a good manufacturing engineer. The proficiencies that were earlier associated with only computer science graduates, for example, programming, computing architecture, data mining, software design, data science, data analytics, machine learning, etc., now are needed to define the attributes for general engineers, not only computing engineers, right? So curriculum mechanism can be flexible. You can teach computing through dedicated computer science courses, or you can include them as modules in discipline-specific courses. For example, MATLAB is a very famous package. We don't teach MATLAB as a separate course. We include it in different courses. For example, some finite element modeling and analysis are major tools. We do have dedicated courses for that, but we include small modules of them in different design and manufacturing courses and so on. Joint task force for computing curricula was made for principal computing disciplines at the university level, and they came up with these: computer engineering, design and construction of computer hardware and systems; computer science, design and application of software and generating solutions for computing problems; information technology, repair and maintenance of computing technology tools and systems for businesses and other commercial organizations; information systems, integration of IT solutions and business processes to fulfill information-related needs of different companies; and software engineering, development and upkeep of software packages and systems, right? So computing curricula could be any of these. And in our engineering curricula, we need all of them from time to time in different courses or as a standalone courses. All of these are now needed in some form in engineering education. So this was that computing skills today are very much required, even if you are not a computer engineer. Now we will talk a little about new pedagogical approaches. Pedagogy means the way you teach, right? That you are very good in mechanical engineering, you are very good in electrical engineering. Are you a good teacher? And to be that, you should be aware of the pedagogical standards in the world. Augmenting basic technical skills with enhanced professional and softer skills is a challenging and intimidating task for engineering educators, right? I mean, usually when we induct people, we induct them more on their publications and research and funding and so on, though we do one or two interviews to see how good they are in communication, but they really show themselves once they are hired. Engineering curricula are already saturated with required courses. But building in additional skills is therefore tough, right? How do we find time to build the additional professional and softer skills? The faculty generally is already complaining of overwork, right? So there is a lack of time and a lack of resources for learning and incorporating new materials and new techniques of pedagogy. Also, engineering enrollments are increasing, right? So the student-teacher ratio is now different. This makes the problem even more demanding. New teaching paradigms and technologies are continuously coming up. They are built around a growing knowledge of how people practice, learn, and teach engineering. You see, how do they practice engineering? How do they learn engineering? And how do they teach engineering? This is developing. Now, coupled with general research on social and behavioral sciences, pedagogical research on student learning, engagement, and motivation is conducted. And there are new classroom and extracurricular interventions that are needed. Some core requirements are: there should be a clear-cut description of student learning outcomes and educational objectives. Before you start a course, you or a team of people should very clearly set forward that these are the learning outcomes of my course, and these are the educational objectives of my whole program. And there should be use of engaging activities. It should not be a lecture-based class only. And there should be a judicial mix of how much you teach and how you assess. Active learning, everybody has heard of it, hopefully. So for those for whom I am sort of repeating it, my apologies. Active or activity-based learning is any teaching strategy that involves classroom activities and an interactive style, especially targeting reflection and contemplation, right? Develop the art of thinking on a certain topic and reasoning and so on. It all started with Montessori education, by the way, right? Those very young kids of KG level and so on, that don't give them lectures, give them activities, and they learn from the activities. So now it has, transported all the way to higher education. It is a simple and yet underlying concept that learning by doing has a higher value. The problem is that you have a certain course to cover, and now you want to add added activities in the classroom. How do you balance the two? Various types of active learning techniques are there. All of these methods encourage independent learning and lifelong learning. That is the target, that I don't teach, you learn, right? I give you a problem, you solve it on your own, and then I'll help you out. So you become an independent learner and a lifelong learner. Some subsets of active learning, one is called problem-based learning. Prompts the students to learn a new topic by attempting to solve a problem. I go to a class, I don't give any lecture. This is a new topic which they have not done before. I give them a simple problem or a semi-complex problem on this topic, divide them into groups, and they try to solve it. Once they have solved it, I give them 10 minutes or so, and then we discuss their solutions. And then my lecture actually starts interactively, right? So as opposed to traditional lecture first, problem later approach, they start by a problem. Collaborative or group learning is another type of active learning, where students interact with each other to solve a problem or achieve a target. It reduces individual competition. When you are working in a group, the whole group is given the same grade, and it builds up team working skills, right? So apart from the technical content, you are not fighting against each other, and you are building team environment. Cooperative learning is another type of active learning. The students still practice collaboration, just as above, but are graded individually rather than as a group. They work in groups, but inside the groups, you still try to grade them individually, and you develop techniques for that. Project-based learning is another type of active learning. It takes group learning to a higher level. The student groups tackle a larger problem and keep working out of the class as well. In the previous cooperative learning, we are giving a small problem in the class. They solve it, finish it there. But if you give them a project for a couple of weeks or for the whole semester, then the whole group works in the class and outside the class, right? Service learning is a relatively new one. It is an extension of project-based learning. In-class instruction serves as a platform to tackle projects that target community welfare, not just engineering problems, but engineering problems that target community welfare. So they are termed service learning. And then real world or experiential education, students learn to handle open-ended and ill-defined problems. Now, these are the most complex type of problems that the problem is not well-defined. It is very ill-defined. You try to find out how we will define it into definite categories. And it is an open-ended problem. There could be many solutions to it. So you generate more than one solution and you try to compare which of the solutions is good. So then there are competing realistic constraints that you work against, economic constraints, manufacturing constraints, and so on. Maker spaces are the end of the active learning thing. There are more focus on hands-on learning. So therefore, for maker spaces, the technology that is in the classroom has to be more advanced and so on, where they could directly work on projects on some systems or machines and so on. One very new thing that came 15, 20, 30 years ago in the world, especially for engineering, is the CDIO initiative. It started in Finland together with collaboration with MIT, the Massachusetts Institute of Technology. Now it is a worldwide initiative. CDIO is conceive, design, implement, operate. So you see, it emulates the design to manufacturing cycle of activities in the real world. He said, if we are teaching engineering, whether it is mechanical or petroleum or civil, how does engineering work? We have a new problem. We think of a new solution. We think of many solutions to it. Then we convert the solution into something realistic, which can be constructed. Once it is done, then we test it. So why should education not be done the way engineering should be done in the field? Conceive, design, implement, operate. So this is one way of looking or relooking at your curricula and see if all our curricula are targeted according to these four basic steps. There is a teaming up of instructors and practitioners, practical field engineers from various institutions around the globe. There is a development of evidence-based teaching practices, evidence-based, that it is not that you are teaching. Whatever projects you are giving, are they really being done in the industry and so on? And there is a sharing of resources, right? If your university or institution becomes a member of the CDIO initiative, then you will collaborate with other institutions around the world in Europe and America and so on. The target is improving of technical knowledge together with communication and professional skills of engineering students. So if you see, it boils down to the same thing, that this is now a new way of looking at things. But what is the target? They have technical skills, they have professional skills, they have communication and software skills, but we are doing it in a different pattern. The use of active learning tools, some as team projects and problem-based learning, is a very basic fundamental. CDIO initiative from the beginning targets active learning environment. So if in the university, the resources for active learning are only a few, you need to develop them before you can join the initiative. The emphasis is again on both core engineering and science concepts, and on top of that, personal skills, interpersonal skills, relearning, and so on. According to the CDIO initiative, there is a division of engineering curricula into four major parts: discipline-specific knowledge and reasoning, personal and professional skills and attributes, interpersonal skills, teamwork and communication, and finally, conceiving, designing, implementing, and operating various engineering systems and machines, right? And in this last one, enough consideration should be given to enterprise, which is entrepreneurship, societal, and environmental impacts, right? That from the beginning, as I said, if you develop an engineering solution, it should not be good only technically. It should be good economically. It should be acceptable to the society. It should not hurt the environment, and so on. So CDIO on one side, I want to talk a little about the enterprise and entrepreneurship, right? That this is now the future, that your engineers should not be trained only to work in organizations. They should be trained to create their own businesses, right? That is how the world will grow. So there is a big difference in producing graduates with a service mindset to work as an employee in an engineering firm with a vision to establish their own technology-based businesses, right? There is a big difference between these two. Entrepreneurial experience for undergraduate students develop a range of business, management, and other professional skills in addition to technical competencies. Now, in my university, we have been trying to do that. It is very easy to say that they should be able to do it. It's a very tough thing, right? We have been trying for the last 10 years, and so we have achieved only, I feel, only 10-20% success. To create entrepreneurship in students is a tough task. As engineers or as educators, we need to be inventors ourselves. We need to be entrepreneurs ourselves, or we need to invite people from the industry who started their own businesses and teach. So it's not something very simple, but this is where the world is going. Entrepreneurship programs or engineering programs with entrepreneurship modules target enhancement of oral and written communication skills, aptitude to think broadly about engineering issues, work in multidisciplinary teams, and have an entrepreneurial mindset, right? So these are the targets. Some universities in the world are now really advanced in this. I know that when I was in King Fahd University in Saudi Arabia, then they signed a contract with MIT for 10 years and so on. And there was an exchange of students and faculty from MIT to KFU, PM, and so forth. And the target was that each group within a year or 2 years will register a patent, right? You will, as part of your education, you will develop some new technique or some new invention, and you will even patent it, right? So then if this type of an environment or collusion or collaboration is there, then yes, you can teach it. Otherwise, you can just teach the basic principles. Graduates of these programs are stronger in leadership and responsibility. They are enthusiastic about setting up their own companies. In the USA, several well-organized support initiatives for teaching of entrepreneurship to engineering and other majors are there. There is a keen program, Kern Entrepreneurial Engineering Network. There is the AP Center program, Engineering Pathways to Innovation Center at the Stanford University. There is the Kaufman Foundation. I am listing them so that if any people who are interacting with us today want to include these things and they want to develop, then these are some organizations which you can directly contact. This would have some free packages also, and so on. One of the things that we want is independent and lifelong learning, right? Purpose of good education is to make students independent learners. Also, learning for engineers cannot stop at graduation. It should be a lifelong process. So once again, I have a quote from Charles West, who is the NAE president in 2012. There is a need for a corporate and national strategy to ramp up the quality and opportunity for lifelong learning for our engineering workforce, right? And we do that. Some universities, alhamdulillah, are doing these retraining programs for the industry, that you are in the industry, you have become old, we will teach you some new computing techniques, some new machining techniques, and so on. So rather than a single course or a certificate, lifelong learning is a new adaptive mindset, right? Adaptive mindset. Individual engineers, companies, and engineering universities must engage in continuing education and lifelong learning. I have been one of those guys who have been in the industry for some years and now in the university. And when I was in the industry, then one of my main thrusts was this, that in every department, technical department, can we do some technical courses to enhance the capabilities of people who are already there. Independent learning and lifelong learning tasks may include literature search and review, independent reading of certain topics, that you don't teach those topics. They are part of your course, but you say you independently learn it. We will have questions and answers on it and so on. open-ended design and other problems where there is no definite solution. There are many solutions which you have to compare. Many projects with written and oral presentations and so on. They should be repeatedly stressed and practiced in different courses. It should not be that lifelong learning is targeted in only 1 or 2 courses. After graduation, engineers can update their competencies through alternative qualifications like diplomas and certifications and licenses, etc. Service learning, right? We talked a bit earlier a little about engineering service means the application of classroom learning and acquired engineering skills to solve practical problems for the community, to tackle multidisciplinary problems, right? You are working on a project which is based in mechanical engineering and electrical engineering and petroleum engineering together and so on. Have a systems approach rather than a very focused approach and understand the broader context and impact of engineering. Experiential or hands-on learning we talked of earlier, it can improve verbal and written communication, teamwork and collaboration, leadership and decision-making and so on. The Carnegie Foundation for the Advancement of Teaching says that undergraduate students should have opportunities to gain international experience, language proficiency, and intercultural aptitude. You just look at it. International experience, language proficiency, not only their own, and intercultural aptitude. So the Carnegie Foundation is telling America and Europe that in your undergraduate program, there should be 1 semester or at least some focus weeks where they work with other countries and other countries work with them. So there is an intercultural interaction also and an international experience. This should be part of engineering education because now engineering is very global. Service learning activities should be an integral part of the degree requirements, should be, whether they can be or not, it depends, because they are based on internships and co-op trainings, right? International exposure, study, work, research, or service in other countries, partnerships such as the International Association for the Exchange of Students for Technical Experience, IESTA. My university is a signatory to IESTA. So our students go to other countries, their students come to us. We can always sign partnerships with them. Service learning programs such as Engineers Without Borders and so on, right? So engineering is now a global market, just not local. And some people would, of course, never leave their country, but many others would. So service learning is very important. Now, with this general background, because we are talking of challenges and so on also, faculty training and faculty development is definitely one major part of it, because faculty who is very well trained technically in their subject, but and traditionally they are good teachers, but have they adapted to all of these new things? A survey of faculty from various institutions was done in 2018 in the US. Surprising and somewhat disappointing results. Engineering and other STEM faculty, STEM, you know, is science, technology, engineering, and mathematics. So they targeted in these surveys, engineering and STEM faculty, show significant resistance in using student-centered teaching strategies as compared to non-STEM faculty, right? Traditional faculty is still very resistant to these changes. And they are generally reluctant to take part in workshops and other activities focusing on new pedagogical techniques. I am now 30 years old already in my profession. Should I start to learn like a student again, right? So there is a big, and this is in the US, the leading technological country in the world. One major reason, faculty who implement innovative classroom practices are generally not given recognition at the time of promotion and tenure rewards. This is very practical, right? Some of us adapt to these new techniques, so we give much more hours, and in the end, if our promotion or our rewards are the same as the other traditional faculty, then we would be discouraged, right? So this is one reason. Engineering faculty are already quite work-stressed, academics plus research. So they need institutional motivation and support in bringing about serious changes in the curricular and teaching methods. So this is now, I am talking to people who are at managerial levels and management levels in teaching institutions and engineering institutions and policy-making places. You want all these changes, you have to have a reward system for that, right? Otherwise, it won't succeed. New teaching and learning strategies and pedagogical method can be included in graduate education programs also, not just undergraduate. The current faculty can learn it through in-house or sponsored teaching workshops. Usually the graduate students doing masters and PhD are going to become your future teachers. So already include these new pedagogies in the graduate program so that the teachers of tomorrow are already trained in this. Training programs conducted by engineering faculty prove to be more effective. They generally include more engineering specific examples and so on. In the US, various national initiatives are now available. Frontiers of engineering education, right? National effective teaching institutes, and so on. Again, if you have a PDF of my talk, then for those policymakers or department heads and so on who want to achieve these things, they can approach these institutions which have a history of 20 to 30 years of working in these areas, and you can help them, especially the last one, right? ASEE, the American Society for Engineering Education. This is the largest world body of educationalists who are in the engineering field. So I will not go through the conclusions. We can list them anyhow. My main focus today was on a very broad topic, that what are the current challenges that the engineering education world faces? What are the new strategies in terms of pedagogy and requirements? And how can the management and the policymakers adapt to it? So I will just skip this. I would definitely like to acknowledge the support of my university, Sultan Qaboos University, for various activities targeting the enhancement of teaching and learning process. As a member there, I have gone through lots of these training workshops on CDIO and active learning and so on, and they really help. And I would leave you with this quotation from Estrada: if a child cannot learn the way we teach, maybe we should teach the way they learn, right? It is not enough to say that I am a very good teacher and that is a bad student. Everyone can be improved. Are we ready to change ourselves? So with that, I conclude my talk today, but I'll just leave you with an invitation, because I think I'm talking to people around the world. Elsevier is publishing the second edition of its 13-volume compendium, Comprehensive Materials Processing. The first edition was published in 2014. This is the second edition. I am the volume editor of the section on thermal engineering of steel alloy systems. So this is an invitation to all of you who work in this area to submit a chapter for thermal engineering of steel alloy systems. The chapter could be a research work, a technical report, or a review article on any topic related to thermal engineering of irons and steel alloys, like heat treatment, surface treatment, laser treatment, and so on. And because we are almost at the closing stage of this activity, so if you are interested, then you can please contact me as soon as possible. So I'll go back to, I don't know. No, I'll go forward. I leave you with a very nice view of Muscat again, and invite you to come there whenever you can. Many a thank.
Thank you, sir, for your wonderful presentation. I would request our colleague that he can just go through the chat. So if we can just look into questions if we have. I would also request our online participants to just type your questions in the chat so that we can ask our resource. I guess there is no question from.
See, I remember one of my very senior professors, after one of his lectures, he said that, you see, if there are no questions at the end of the lecture, then either the lecturer was perfect, which I definitely know I am not, or that nobody understood anything. No, but so, yeah, that is just.
But I know few people that they are from Nigeria, Uganda.
Yep.
And because some of the names are similar to familiar to me. Yeah, because we have a program of Alliance of Islamic Universities of Africa.
Good.
And there are a few colleagues from there. And I am sure that because we had a meeting last month and we had over 18 vice chancellors from Africa.
Whoops, mashallah.
And the aim of that meeting was to encourage them and support our brothers in Africa to develop different programs of science and engineering in their universities.
Good.
Specifically, we are also aiming for a project in Chad to develop the faculties of science and engineering there. So after your comprehensive talk today, I'm sure that we could be your presentation and your experience would be very helpful in developing the faculties itself in some universities in Africa.
Well,
So I would encourage our participants, if you have any question from presentation. Yes.
Some are there.
Yes, I'm asking a question regarding the switch up in degrees after graduation. Can those people switch from natural sciences to engineering and master's degree? They can contribute as much as those who graduate as engineers.
Well, a very thought-provoking question, but yes and no, right? There is no definite thing. I know one of my friends, he graduated from Harvard Medical, the place in medical. And after working for 2 to 3, 4 years, I don't know, he got fed up. He went back and did an MBA. Again, Harvard MBA is one of the top. So some people, and then he shifted to management of hospitals rather than working as a direct. I know a daughter of a colleague here in Islamabad. She started as a doctor in oncology, and now she is the deputy administrator at Shifa. She shifted and did a master's in medical administration. So sometimes, yes, this can be very fruitful. It depends on the environment, but it depends on the person, definitely. Even very later in my life, I can decide that I don't like this field. So why should I continue working for 30 more years in that? Or I can feel that though I am an engineer, but engineering can be applied in so many other places, and I shift to social sciences and apply my engineering problem-solving skills there. So as I said, the answer is yes and no. It can be very successful, or it can end up a little differently. Hopefully, I have answered you.
In continuation to this question, I would ask
that
I had gone through few examples that few engineers did their MBA after that. And as you were talking about entrepreneurship idea, so does it complement to engineers going into the business and marketing part?
You see, MBA, if you know, right, has different areas, right? You do an MBA in marketing, or an MBA in finance, or an MBA in management itself. So which MBA did you choose is one thing. Mostly engineers would choose an MBA in management, that they would want to rise higher in the hierarchy, that after a certain level of technical expertise, they don't promote you anymore. They said you should have a managerial background. So generally, it is a good combination to have engineering plus MBA, but generally not in finance, perhaps. Unfortunately, in general MBAs, apart from very new programs, they don't teach a lot of entrepreneurship. This innovation thing is different. So if there is an MBA which has at least some portion of entrepreneurship, then it would be great, but it depends on the program you choose. So yes, engineering and MBA are very common, and many of my friends have done that, and it helps you run your company in a better way and so on. But then after engineering, for example, my son is a civil engineer. So I am advising him that, if he does not go for a PhD and so on, that's his choice. But he wants to limit at master's level, then rather than an MBA, I would like him to do a degree in construction management. So it is management focused only for the construction industry, rather than having general, right? So you can make those choices yourself, and you can take advice from senior people if you like.
So moving on to the next question, how can you integrate artificial intelligence in training of pharmaceutical engineering?
Whoa. You see, this question, you remove pharmaceutical from there, write anything there. In the training of mechanical engineering, in the training of industrial engineering, in the training of petroleum engineering, the answer will be the same, isn't it? That AI techniques should be included in your curricula. This is the first requirement. In our university, in the last 2 years, we are going through what we call modernization of undergraduate curricula. And it's a very tough task, right? We have 134 credits. If I want to add something new, I can't just add a course. This is too much burden. So what should I remove to add something new? It's a very, very challenging task, and we have been doing that. But we have just added a new course, not a new course, a revamped course. Previously, we used to do an engineering programming course, right? Whether it was C++ or Delphi or something. So now, rather than that, we have added a course on data analytics. Now, data analytics means some machine learning, some AI is built into the course. So they will be learning programming through some very modern language, but they will be directly doing it in sort of an AI-based environment. Of course, at undergraduate level, that will be only one course. So now the other courses that are there, if I'm teaching design, can I give them some problems which are AI-based? If I'm teaching them manufacturing, can I do some courses or some exercises where they're AI-based? So now the training of the faculty is required before we do this to the students, or we induct 1 or 2 new faculty. So whether it is pharmaceutical engineering or any others, if you want to integrate AI, then your teaching faculty has to have a background in that, and they have to add small modules in different courses.
Thank you, sir, for your comprehensive answer.
Yeah, that's okay. The next question is the same. How can you integrate artificial intelligence, right?
That's
in
same.
Pharmaceutical engineering. So same, yes.
Regarding the copy of the
slides,
slides, we'll send you over email.
Yeah, I can do that.
We'll send it to the registered party.
Yeah, I would prefer to send it as a PDF because this format will, not interact very well. So we can do a PDF of that, and then you send it. It is easier. It goes without hindrances. Any others? Can we scroll down? Oh, this is the end.
This is the end.
Good.
So thank you, sir, once again for your wonderful lecture here today at Comstech. So I would request Professor Khurshid to give you a souvenir on behalf of coordinators in Comstech.
यहाँ से कोई सवाल या कोई तबसरा? What? Now we can face the audience.
This is more of staff.